Okay, so in this lecture, we'll be talking about DFS, that is the depth first search, and DSU, that is a disjoint set union. Now we'll be talking about all of this stuff from the very scratch, right? You don't need any other prerequisite rather than basic recursion for this. This would be a friendly lecture. We'll be talking of DFS. We'll solve a question from code forces using the DFS traversal, and then we'll also talk about DSU. So I'll explain you the concept, and we'll also try to code it up, and we'll talk about it. I'll take your reviews whether you think it's a hard concept or not, and then we'll talk where all we can use this. So where all we can use DSU. So that's the motivation for this lecture. So for those of you who actually don't know what graph algorithms are, so try to consider graph as a set of nodes and edges, wherein each node or some nodes are connected via edges. So you can think in terms of cities. So let's say this is a city, this is a city, this is a city. And when we are showing a edge, so this can be a road, right? So you can go from 1 to 5, you can go from 1 to 3 or 1 to 6. You cannot directly go from 1 to 7, right? There's no road over here, but you can go from 1 to 3 to 7. So try to think in those terms. That would be helpful. So right now I have this amazing, not like amazing video, but yeah, basic video which can actually tell you that how a DFS traversal works. So when over here, if a node is colored white, that means we have not visited it, right? If a node is colored red, it means we are on that particular node. And if it's visited gray, then that would mean that we have already visited it. So initially, everything is white except for 1 because we are on the node 1 right now. So let's see how it works. So from 1 we go to 3. Now 3 became red, and then from 3 we are going to 5. From 5 we get into 7. Now we reach 7 and we'll realize that I don't have any other neighbor, or I'm not connected to anything that is unvisited, right? So 7 is not connected to any unvisited node. So it'll say I'll go back to 5. So it will go back to 5. 5 would go back to 3. 3 would then say, do I have a neighbor which is unvisited? So yes, 3 has 6, right? So 3 would say I'll go to 6. So 3 goes to 6. 6 goes to 2. 2 goes to 4. 4 would go to 10. Then we'll again traverse back, because we'll say that okay, there's no connected edge or a connected node that is not visited right now. So from 10 back to 4, back to 2. Then 2 says okay, 8 is edge that I have. Whose mic is on? Guys, can you mute the mic if you're not having a doubt? Chetan, can you mute the mic, please? Cool, thanks. Okay, so from back to 2. From 2 we'll go to 8, because 2 will say that okay, I have a node in my vicinity, or I'm connected to a node which is not visited, so let's visit that. So from 2 I'll go to 8. Then I'll start going back, because now I'll say okay, no remaining nodes in my vicinity which are not visited, so I'll go back. I'll go back to 6, I'll go back to 3, I'll go back to 2, I'll go back to 1 then, right? Now I'll say I'm back at 1. Now do I have a node which is still not visited? Yes, I have 9. I'll go over that. Then I'll go to 11, then to 12. Then I'll come back, right? So this comes back to 3, or back to 1, and then we say every node has been visited, right? So that completes the DFS traversal. I know that was a bit fast, but let's try to understand how it works. So you guys want me to explain it a bit more, or the video was helpful? How shall we go about it?
I understood.
You understood? Yeah. So
Yep.
you are in the first year. I'm assuming if you understood, everyone else would have
Yes.
understood. Okay. So a bit more, right? Cool. Let's talk about it a bit more then. Okay. Good. So what I'm saying is that you are at this node, right? You are at this node. This is node A. Let's say node A is connected to a node B. It's connected to a node C, and it's also connected to node D. Then node D is connected to something like E, right? Now we'll start. Now where do we start from? Let's say we start from a node A. So we can start from any node. We'll start from node A, and then I'll say what are the nodes to its vicinity that are unvisited right now. So initially everything is unvisited, right? So there are 3 nodes in its vicinity that is unvisited. I can start with any one of them. So I'll say okay, I'll start with C. I'll go to C. Okay, so this node is actually visited right now, because this is the first node we are starting with. So as soon as you are on a node, you'll mark it as visited. So you'll mark it as visited. Cool. Now you'll come to C. You'll say that okay, this is also visited now. Do I have any child, or do I have any node in my vicinity that is not visited? So C does not have any node in its vicinity. It only has one node, that is A. and A is also visited. So it will say that, okay, I don't have any nodes in my vicinity or in my connections that is not visited right now, right? So it will say, okay, I don't have any node. So the traversal would go back. While going back, so we'll follow the edge from which we came. So we'll go back to the same node. Now we'll say that, okay, I'm at A. Where should I go now? Go to any of the unvisited nodes. So the unvisited nodes you have are D and B. So you'll say, okay, I'll go to D. You go to D, you mark it as visited. This becomes visited. You ask D, is there any node in your vicinity that is not visited? D would say that yes, E is a node in my vicinity that is not visited. Cool enough, let's go to that. So you'll go to E. You'll say that you'll mark E as visited. And then you'll say that, okay, E, do you have a node in your vicinity or in your connections that is not visited? E would say, I don't have any nodes. The only node I was connected to was D itself. And that is also visited. So let's go back, right? So we'll go back along the same path we came from. So this was the path we came from. So we'll go back to the same path. We'll come to D. And at D, we'll ask him again, do you have any nodes that are not visited and are in your connections? D would say, no, I just had A and D and both of them are visited now. So let's go back. We'll go back to A. We'll ask A, is there any node in your connections that is not visited? It will say, yeah, I have a node B that is not visited. Let's go to that. Right. We'll come over here. We'll mark it as visited. We'll say, okay, B, do you have a node in your connections that is not visited? So it will say, yeah, I actually have A, but A is also already visited. So I don't have any. So let's go back then because you don't have any nodes. So let's go back. You'll go back like this. You'll come back to A. You'll ask it, A, do you have a node right now which is not visited? So it'll say, no, all my like nodes that are connected to me are already visited now. So let's go back. But where should I go back? So this is the node we started from, right? So our traversal completes over here itself. Make sense? Guys, make sense?
Yes.
Okay, if there's a doubt, let me know. Okay, bit more how to maintain visited nodes under unordered set or something else like class node has at, yeah, cool. So there are multiple ways of doing it. If you want to make a class and then set it as an attribute, that is doable, but it's not advisable to do that in case of CP and stuff because the time constraint is always there in CP, right? So what you should rather do is you can make, okay, so I was gonna teach it anyway, but okay, so what you can do is you can make a visited or a boolean vector or an array, whatever you want to make, called visited, right? And its size would go from 0 to n, where if your nodes are numbered from 0 to n minus 1, so its size can go up till n, right? And whenever, so initially all the nodes would be set to 0 because we'll say that they are not visited, and as and when you visit a node, you'll mark that as 1. Other ways of doing it is that you can use an unordered set, or you can use a hash map. You can use anything you want, but this by far is the fastest. If your nodes are actually numbered from 0 to n minus 1, then this becomes faster, right? Now let's say you had some nodes that were spread across different numbers. So you had nodes that were spread across, let's say 0 to 10 to power 16, but they were spread across, let's say there was one node named 1, then there was some named 5, then maybe 100, then 10 to power 5, something like of this sorts, right? Or 10 to power 6 or 7, something of this sorts. Then in that case, you would have definitely taken an unordered set, right? Or you could have taken the you could have taken a unordered map wherein the first value could have defined the node name or the node ID. The second ID column would have defined whether it's visited or not visited. That makes sense? Okay, so if there are no questions, yeah, cool. So let's move ahead. So I want to teach you the implementation, but what I'll do is that I'll start from the very basics, right? So I'll remove all the code. Let's try it from the basic itself. So let's say we are talking of a graph. So let me make some changes over here. Yeah. So in a graph, you'll have some nodes. Let's say this represents your nodes. How many nodes you have? Int nodes equal to 0 initially. And let's give it some random value right now. Let's say these are the nodes that you're having. You are just having 5 nodes, right? Okay, so we can remove the scene now. Now, how do we represent this particular adjacency list? So over here, you have this list, right? Where you have to tell that A goes to C, A goes to D, A goes to B, right? How do you represent it? So there are multiple ways of doing it. One way is that you can have a matrix. Okay, so matrix, cell, any cell in the matrix can be denoted by ij, right? For example, this is 0 0, this is 1 1, this is 0 2, right? So ij basically represents whether there is an edge from I to j. So that's one way of representing it. Because we are using a matrix, we'll be able to define that, okay, do I have a particular edge from I to j? If we don't have that edge, all of that sorts. The the problem with this approach is that, let's say you are having n vertices, right? Then the size of this matrix goes up to n square. And in case we are having a sparse graph. Now, what do I mean by sparse graph? So this is a graph, right? Okay, so just a connection of nodes and edges is actually a graph. This is a graph. This is kind of a sparse graph because the number of edges are not that great. So the number of edges over here are 1 2 3 4 5 6 7, right? So there's just 7 edges, and the number of vertices were 1 2 3 4 5 6 7 8. Just 8 nodes. Okay, then edges would also have been 8, but anyway, so the number of nodes and edges were somewhat similar, but the total number of edges can actually go up to order of n square. That is called a dense graph. Let me show you example. Now let's say in my graph, every node is connected to every other node. Now let's say these are the 4 nodes. They are connected like this. Okay, and this would be connected by this. If that completes it, right? So in this kind of a graph, let's say you were having around 100 edges, right? So you'll be having, okay, 100 nodes, and every node was connected to another node, right? So in totality, you'll be having n into n minus 1 by 2. That gives you 100 into 99 divided by 2. Okay, that gives you 50 into 99, right? So that number is pretty huge. Now let's say you had 10 to power 5 edges or 10 to power 5 nodes. Then this matrix or the adjacency matrix would take a space of order of 10 to power 10. That's gonna give you a MLE or a TLE, right? MLE or a TLE. So this cannot be used. I hope I'm not rushing the things up and you're able to understand it. You can okay, sir, can you zoom a bit? Bro, I cannot zoom this thing. I can zoom the code. Would that work? Hikaku, would that work? Okay. So yeah, I'm also hoping that I'm not speeding the things up. If there's anything you're not able to understand, you can point it right over there. Yeah, the code section I can zoom. So let me just do that so that I don't forget it. Okay. Is this fine? Okay, we'll wait for, yeah, cool. Okay, so back to the iPad. Yeah. So over here, adjacency matrix or ADJ matrix takes order of n square space complexity as well as order of n square time complexity to build up. Now, in case you are having a sparse graph, over there the edges would actually have been an order of n, right? But anyway, to build this, you are taking order of n square, so it's gonna give you a TLE. The other way of doing it is adjacency list, right? Now, what's the adjacency list? Let's say I note down all the numbers. So I'll note down 0, 1, 2, 3. Let's say I just had 4 nodes having these indices 0, 1, 2, 3, right? So what I'll do is I'll say that, okay, 0 is connected to which all nodes. So I'll say that, okay, 0 is connected. Okay, let me draw it with a different color. Okay, so 0 is connected to node 1 and node 3 maybe. 1 is connected to node 2. 2 is connected to nothing, right? 3 is connected to node 0, let's say. So this is one way of representation. Now over here, the space it takes me to represent this is only order of edges or the number of edges I'm actually having. So this is one of the most utilized approaches in case of CP. So most of the times when you'll see a question, you are gonna use an adjacency matrix. So let me tell you, how do you represent an adjacency matrix or how do you code that up? Any doubt so far?
Nope.
Cool. Okay. Okay, yeah, just one more thing. So some people are actually not using their mic. So in case those people have a doubt and they type over here, so please let me know, like whosoever is using the mic, just speak up and let me know that someone is having a doubt and I'll just check the chat. Cool.
Yeah,
So
okay, I'll check.
yeah, thanks bro. Okay, so what I'm saying is that I want to define an adjacency matrix or adjacency list. So I'll call that would be a vector of vector, right? Let's call it ADJ. Let's take the number of edges. So let's call it edges. and initially it's 0. I'll ask the user for how many edges do you have, right? Then for each of the edges I want to know whether from where it's going to where, right? So I'll ask the user for two inputs, u and v. That would mean there's an edge from u to v, right? And then I'll represent that using my matrix. So u dot pushback v. But since there can be two kinds of edges, so there could be a bidirectional edge and a unidirectional edge. Now what do I mean by that? Okay, so over here we were saying that, okay, we were saying that from A we are going to B. Now is it the case that we can only go from A to we were going from A to C, right? So is it the case we can only go from A to C, or we can go from C to A as well, right? So if we can only go from A to C, that means this is a unidirectional edge, right? If we can go from A to C as well as from C to A, that means this is bidirectional. So this is working at both the ends, right? So in case your edge which you are considering, if that is unidirectional, this would work. Cool. If it's bidirectional, then you'll have to say that, okay, I'll have to have a back edge as well. So this would be the thing you'll require, right? This is for bidirectional edges. For now, let's just keep it for unidirectional edges, right? And then we'll say, okay, after this, you would have already populated your graph, or you'll already know what your adjacency list is. Let's just make it more pertinent. So let's call it adjacency list, so that we exactly know we are having a matrix or a list, right? That's it. So that's how you populate a graph. I know it seems easy, but that's it. I can't make it complicated if it's easy, right? So that's how you take a graph from the input. Now let's try to traverse it. Now we'll go for DFS traversal. So what all components do we need to know that where I'm standing at my where I'm currently standing, or which node I'm currently standing? So I definitely need to know the node index. So let's call that node. I also need to know that adjacency list, so that I know where all I can go, right? What more? So there's something called a vector visited I need, or let's call it a bool, right? Okay. So over here, let me also define a boolean vector. Let's call it visited, and the size would be n comma 0 or nodes comma 0. Okay. So a boolean vector of five nodes, or of five units, or 5 elements, all of which are set to 0 currently, right? So this looks cool to me, right? Let's just see if it has a bug in it or something of that sort. Let me see. Let me just, yeah. Okay. Let's just run all. Okay, it's giving a bug. Why it's giving that? Okay, I'm using a in DFS. Let's do it a void DFS. Cool enough. Let's try it again. Run all. Cool. So the code is perfectly fine. Now, how do we go about the DFS thing itself? So firstly, when I come to a current node, I'll say that this node is visited, right? So this node would now become visited. Then I'll say I want to check what all nodes are connected to me. Now, the nodes that would be connected to me would be present in that ADJ list, right? On in this particular list itself. So I'll say that, okay, I want to get the nodes that are my connections. So connections are in the ADJ list of this node, right? Okay, I messed it up. Yeah, cool. Okay, so once you're over here, there could be two scenarios: that the node you're talking about that was in your connections, it's already visited, right? So if the connection node is already visited, then continue. Okay. Okay, but over here, this would anyway work, but if you just want to add more checks, you can say it's equal to true. It actually means the same thing. If it's not true, what do you want to do? So now you found a node that is in your connections, but it's not visited yet. So what would you do? You'll say that I want to visit it. So let's go to that node. Let's go to the connection node. The rest parameters would remain the same, adjacency list and the visited array, right? This would be your code actually. Now this code actually is not performing anything. It's just visiting it, but it's not even telling us about the names itself. Let's populate some names, right? So let's say whenever we get to a particular node, let's just print the node ID. Okay, I am at the node. That is node. Make sense? Now let's give it some values. So over here we have the adjacency list, but we have not populated it. So let's see, let's try to make a graph and we'll populate that. Cool. Okay, let's try to make a graph now. So we'll be having a graph of, let's say, just 4 edges. 4 edges would do fine for me, or 4 nodes, right? So this is the node 1. Okay, this is the node 1, this is 2, this is 3, this is 4. That works. Let's connect the edges. But since we are computer science engineers, let's use 0-based indexing rather than 1-based indexing. So that's what I'm going to use. So the graph is of 0, 1, 2, 3. Let's connect some of the edges. So I'll say that, okay, from 0 I can go to 1, and over here we were talking of unidirectional, so I'll be talking in that form. So from 0 I can go to 1, from 1 I can go to 2, right? And from 1 I can also go to 3. Make sense? Fair enough. Let's try to give this particular graph to my system. Okay, how would I do that? So the simple way is, firstly I'll tell that how many number of edges are there in my graph. So number of edges are 3, right? And the edges are that from 0 I can go to 1, from 1 I can go to 2, from 1 I can go to 3. That's it. And over here I'll have to change, because the number of edges were actually hard coded, so I'll change them to 3 now, or 4, sorry, 4. So we have 4 nodes, or I can actually populate it. Okay, let's populate it by user count. So okay, nodes. So we'll say that, okay, I am having 4 nodes and 3 edges. From 0 we are going to 1, from 1 we are going to 2, and from 1 we can also go to 3. Now let's run a DFS on it. So when I'll run a DFS, I'll say, where do I want to start from? So I'll say, okay, I want to start from the 0th index itself, right? Then what's the adjacency list? So adjacency list is given by ADJ list. And what's my visited boolean vector? So that's called bool. Visited. Let's try this out. Let's see what it gives us. Okay, it's giving us a seg. Weird. Now we'll have to see why that's happening. Okay, give me a second. This seems fine. Shouldn't be a problem with this. We are going to our DFS array. We are saying
Maybe the adjacency list, maybe you need to declare size of it.
oh yeah,
You took a note as
yeah,
in.
right. No mistake, but yeah, thanks. Okay, but this actually shows me that you guys are actually attentive in the session itself. Let's see. Okay, cool. So it's showing a wrong answer because I didn't given it any expected output, but the answer is completely fine. So let's see what it's doing. So it's saying that firstly I went to 0. That's fine because you started at 0. Then it's saying I went to 1. Then it's saying I went to 2. Then it's saying I went to 3. Let's see why that's happening. So initially in the graph itself, it was at 0. So it printed 0, right? It printed 0. Let me change the color. Okay. So it printed 0 over here. Then it went to 1. It printed 1. Then it said that, okay, I'm at 1 now. And there are 2 ways I can go. So I can go either to 2 or I can go to 3, right? So I could have selected any one of it. Now my PC wanted to select one of the nodes, and the way it would have actually selected is that it will say that which nodes were added earlier because it's a vector. So it would have said that. Now if I change the order over here, right, the answer would also change. Let's just try this. Okay, so now you say it says 0, 1, 3, 2. Now why that's happening, I'll tell you. So then it said that, okay, from 1 I can go to 2 initially, right? So it said, okay, I'll go to 2, I'll print it 2. Then it'll ask you that, do you have any node in your connections that is not visited? It'll say no. So we'll go back, right? Now we are at 1, and it'll again say that, do you have a unvisited node in your connections? Yeah, I have 3. So let's go over here, right? I'll go over here, I'll print a 3. Cool enough. So 0, 1, 2, 3 makes sense. But why did we get a 0, 1, 3, 2 in the next scenario? Any guesses, or if someone paid attention to that?
Because we changed the order, right?
Yep. So what?
In adjacency list, 3 will come first.
Exactly. So great. Okay. So what actually happened is that in our adjacency list, we were having this kind of order, right? So this was adjacency list. This was 0, 1, then 2 and 3, right? And then it will say saying where it's all connected to. So initially we told it 0 and 1. So it said, okay, I'll add 1 over here. Then we said that 1 is connected to 2. So it said, okay, 1 is connected to 2. That's fine. Then we said that 2 is connected to nothing. So it did nothing over that. Then we said that, okay, 1 is connected to 3 as well. So it pushed 3 over here. But in the second scenario, when I change the input, so now this input produced the answer 0, 1, 2, 3. But then if I change the way I give it the input, so if I said it that okay, so if I told it that the input is 0 comma 1, so it will do this, right? Then I said that okay, 1 comma 3 is one of the inputs or one of the edges, then it would have pushed 3 over here, and then it would have pushed 2. So while traversing also, firstly it would check this. So if it would have checked this first, so it would have gone over here, it would have printed 3, and then after coming back it would have printed 2. I hope that makes sense. Any doubts so far?
Yes, sir.
Okay, cool enough. So
Slip no,
क्या हो गया?
no, sir. No, sir. Continue, continue.
Okay, cool, bro.
No issue.
Cool. Okay, so one more thing. Now we talked about unidirectional, right? What if the things are bidirectional? So if I can go from U to V and from V to U, let's see if the things actually change over there or it exactly remains the same. Let's just test it. Okay, yeah. Okay, so it still remains the same. Now, why is that the case? Because it doesn't actually matter if you're taking a unidirectional approach or a bidirectional approach. It might matter in some scenarios. So, what do I mean by that? So let's say there was a node there was another value over here that was, let's say, 4, and then 4 was connected to 2 like this, right? Then bidirectional would have still given us the similar answer. It would have given us 0, 1, 2, 3, and then maybe 4, right? But if we took unidirectional, then it would have gone to 2, and then it would have said that okay, from 2, 4 is also like I can go to 4 also from 2. Then the answer we would have got could have been different, like 0, 1, 2, 4, 3, right? But since there were no cycles in the graph, hence the answer remained the same. Make sense? So the only thing when the question asks you that the graph you're provided with is actually bidirectional, so the only thing you need to take care of is that you need to add a reverse edge as well. So if the edge is going from 0 to V, and if it's bidirectional, then the edge also would be going from V to U. So this is something you need to add over there. All of this makes sense? Guys,
Yes.
any questions so clear so far? Abhay, what about you? You're the, I guess, the only guy from first year over here.
Yes,
So you must
I
be.
understood most of the things.
Was there something you didn't understand?
I don't think so. Yeah.
Okay. Yeah.
I'll just have to try and implement it myself once.
Yeah, that's fine. So whatever I'm teaching over here, I actually would like that you go and try to implement it on your own, because no matter how how attentive you try to be, but if you haven't coded on your own, it's not like a good concept in your memory till the time.
I did try one another implementation just now.
Mm-hmm.
Wait, I'll show you.
Okay, cool. By that time, is there anyone else who wants me to cover something or has a doubt? Okay, cool. So, Abhay, you can share your code or whatever. Okay, you shared it. Uh-huh. Yeah, this is fine too. I hope that, okay, so children which are using over here, is this a vector or what? Okay, you shared the entire thing.
It's an array. I just push children inside the tree.
Okay, so the problem would be that how would you dynamically manage it?
Yeah, exactly. I cannot use the tree to traverse it again because every node is already visible.
No, 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 not even that. So what I'm saying is, if you want to dynamically manage the edges, right? So right now you are having a node, and in that node you are initially saying that its value is set to. Okay, so this would say that no children are over there, right? Now you want to set some children into
Yeah.
that. How would you do that?
I manually put them
Okay, okay,
for
cool.
now.
Got it. Yeah,
Yeah.
so don't use this particular approach. This is good if you want to show some interviewer about the thing, but whenever you're doing CP, stick to this approach, I'll say. Unless you
Okay.
discover something better. So you can stick to this approach. The code is simpler, it's
Okay.
much more shorter, right? So this actually makes a lot of sense. Also, I do have a snippet. Okay, so Okay, so see, I have a snippet called grinp. If I use it, so it automatically generates the entire graph for me. So you can utilize snippets like of these sorts, but stick to these kind of implementation which are easier to use in case of CP and contest, right? Are you already giving some
Yeah.
contest at this moment?
Like no, 1 year ago I gave Google Kickstart.
Oh, you should actually try
Yeah.
contest, right? Do try.
Yes, I'll try. Like these days my exams are going on, so I am not giving any contest, but I'll surely try.
Cool enough. So let's try to see a question and let's try to see how can we convert a particular question into a DFS question. Now, what do I mean by that? So it's not always the case that you'll get questions wherein you are given a adjacency list and you are given some nodes and then you'll make the graph in this particular fashion. There could be cases wherein you're not given anything of that sort. So you're just given a plain and simple question. You have to realize that how can you convert that question into a graph problem and then solve it. Now I'm talking of this question. This is actually a very, very simple question. It's, I guess, a 800, 900 level problem. Yeah, it's a 800 level problem. But the reason of taking this question is because obviously it's solvable in a greedy approach or by simply looking at the strings. But I wanted to show you how to convert a problem into a DP problem or into a graph problem, right? So I'm going to show you how to convert this into a graph problem. So the problem states that Monocarp is playing a computer game. Now he wants to complete the first level of his game. A level is a rectangular grid of 2 rows and n columns. Monocarp controls a character which starts in cell 1 1 at the intersection of the first row and the first column. So yeah, I'll explain that a bit later. And then Monocarp's character can move from one cell to the other in one step if the cell are adjacent by a side or by a corner. So it's not just that you can go to the side, you can also traverse diagonally, right? Formally, it's possible to move from this cell to this cell if the difference between the x coordinates and is less than equal to 1 and the difference between the y coordinates is less than equal to 1, and obviously it's prohibited to go outside the grid. And there are some traps in some cells. If Monocarp character finds himself in such a cell, then he dies and the game ends. To complete a level, Monocarp character should reach the end cell, that is 2n, right, at the intersection of the second row 2 and column n. Okay, then they have provided this thing, and then they have also given an additional constraint that your first cell and the last cell are actually always safe. Now let me try to draw this thing for you so that you understand this better. Okay, so we'll be provided with a matrix or a grid, and this would be a 2 into n grid, right? So there are 2 rows and n columns in it. You will be starting at this particular column. They are calling it 1 1. You can call it 0 0 if you want zero based indexing, and you need to go to this particular index that basically is 2 comma n, or you can call it 1 comma n minus 1 for zero based indexing. Okay, so how would you do that? Let's try to figure out if there are some steps that are useless for me. So going back is definitely useless. So standing at a particular index, let's say I'm standing over here, right? Going back is definitely useless. Going at the bottom is definitely useless. Now why is this the case? Because anyway I want to move ahead, right? So I can go over here or over here, right? But if I'm going to this particular index that is just beneath me or just at the top of me, then in the next step also I'm going to go to my right. So this step is actually useless. It's of no use to me. So the only 2 steps that would actually make sense is going to my right or going to my diagonal bottom or my diagonal top if this is a valid cell over here. So these are the 3 steps that actually make sense to me, right? Or to formalize it, what I can say is from any cell. So if I'm standing at the ith column, right? So I could be at cell 0 or at cell 1. So I could be at like I comma 0, or I could be at I. Okay, so it's not I comma 0, it's the other way around. Yeah. So I could be at 0 comma I, or I could be at 1 comma I. The only possibilities for both these scenarios is that I want to move to another cell that is either 0 comma I plus 1 or 0 or 1 comma I plus 1. So far so good. This makes sense. Guys, this makes sense to you?
Yes.
Yes.
Okay, cool. So far so good. Let's move ahead. Cool. So can we think of this in terms of a graph problem? Now there's a basic thing that you can utilize over here. So you can say that instead of cells, so basically in the grid you have cells, right? You're having cells. Let's think of these in terms of grid, in terms of nodes. So these are your nodes now, which initially were cells like this. Okay, which initially were like this. You were having like grids, and these were your cells. But now what I did is I removed the grid itself. So I removed this entire structure. So it now becomes nodes, right? And how are these nodes connected? So these nodes are connected in a way in which I can traverse them. So let's say this is connected to this and this, right? And this is also connected to this and this, because I said that the only two ways that actually make sense for me to traverse on is either going to the right element. I can go to the right element at the 0th location or right element at the first location, but I'll have to go to the right. Similarly, this is connected to this and this, right? Similarly, this is connected to this and this. This is also connected in this fashion. Make sense? Okay. So with this in mind, what I can say is I'm going to start at this particular node. That is something I already know, right? Let's call it DFS traversal over here. So let's call this as my X index. Let's call this as my Y index, right? What I'll do is I'll start a DFS traversal. I'll check that if the node to my right at, let's say, 0th location. So what I'll do is that if my graph, or if my matrix at x plus 1, not x plus 1 but 0 comma y plus 1, right, if it's not equal to 1, now 1 actually denotes that it is a trap. So they have actually mentioned it over here that your node 1 would be if the value is 1, that means it's a trap, right? So if your value is not equal to 1, then in that case you can traverse it, right? Or if your matrix and the value 1 comma y plus 1 is not equal to 1, in that case you can traverse it, right? So these are the only two cases in which you can traverse them. Now when you're traversing it and you're able to reach the end, then only you'll say that I've achieved the goal, else you'll say I have not achieved the goal. That's basic stuff, right? Let's try to see this in implementation. Let's try to see the code for this. Let me try to code along. Okay, cool enough. Let me clear this up so that we code from the beginning itself. So firstly, they are providing me with two strings. So I'll take them in, like I'll just consider that them as a matrix, or matrix vector of string v, whose size is basically 2, right? They're just two strings, or they're just two rows in total, right? Then I'll take the vector itself. Now the reason I'm able to take the vector itself is because of this input output thing I've added, right? Okay, so after that I'll call a DFS call, but let's just define the DFS call first. Now what do we want this DFS to return us? I want it to return us a boolean, a value 0 or 1, depending on whether I'm able to reach the last cell or not, right? Now bool DFS int x, int y, right? And then I'll say vector int, okay, sorry, vector of string mat. Now if your x is equal to the last index, right, and y is equal to 2.
Someone is asking, can we also solve using this DP?
DP is actually not required. So yeah, can we solve this using DP? You can actually just do a simple observation over here that whenever in both of the strings at the same location you'll have a 1 1, that would create a blockage, right? So if that kind of a scenario happens, you have to return 0. So for example, there's no 1 1 directly related over here, so it's a yes. Nothing over here as well. Over here you can see that 1 is over here and 1 is over here as well, right? So that's a no. Also 1 was over here, 1 was over here, that's also no. Over here you don't see any such trend, so it's a yes. So DP is not required. Yes, you can utilize DP, but it's just I'll say overkill. Even a DFS is a overkill for this, but I wanted to explain you how to convert the question, and that's the reason of explaining this logic. Make sense? James, make sense? Cool. Okay, so let's move ahead. So what I'll say is that if I'm at the last node, right, then I'll return true, right? If I'm not at the last node, or I did not even need to mention this. Anyway, cool. So if I'm at the last node, good enough. Else what I'll do is that if the next element to me, so the next element would be given by uh, the element at the top, and to the right would be given by matrix of 0 and y plus 1, right? So over here it had to be y. Cool. If it's not equal to 0, or if it's not equal to 1, sorry, that 1 was actually denoting a trap. So if it's not a trap, right, then I can go over that and I'll return whatever the DFS gave me for that. So I'll say x is actually 0, y plus 1, right, and then a matrix. The other case is if my first element to my right, if it's not equal to minus, if it's not a 1, that means if it's not trap, then also I can do that, right? So I'll say DFS 1 y plus 1, right, and mat. Cool. What next? So if both of them were trap, both of the digits to my right were trap, then in that case I'll definitely have to return a 0 because there's no way there's no place I can go to. That makes sense, I guess. Over here I'll just see that if my DFS starting at the point 0 and 0, right, if it's returning the okay, instead of a mat I'll have to provide a v. Yeah, if it's providing me a true value, then I'll print a yes, else I'll just print no. Let's see if it works. Okay. That was a lot of changes. Give me a second, let me resolve this. Okay, yep, let's copy this, let's just populate it again. Cool, sounds cool to me. Let's see. Cool, so this worked, right? Let's try submitting it. Cool, it got accepted. So this is a general way you can convert problems which are not typically given in terms of graphs to graph problems. Now for this problem, this definitely was an overkill. It was not required for us to convert into a graph problem. It could have easily been done by a simply going through that entire string once. But I just wanted to teach you the concept that how do we do it. So was this helpful? And do you have any doubts? If
Yes.
not, we are going to go to the next concept. But if you have a doubt, shoot it right away.
Like we should return or of both the answers, na? Like there, can you move to your code?
You could have done that, but it's not required. If you would do that, the complexity would actually increase because you have to understand that over here in this code, right? Okay, I got your point. What you're trying to say is that we can go to the 0th to my left or to my 1th to my left, right? So we should have tried for
Yeah.
both of them. But the thing is that it would have increased the complexity. Now, how would it have done it? Okay, so let's say that your string was something like, let me show you. Okay, so you had this kind of a string wherein there were all zeros, right? So 0 0 0 0 0 0 0 0 0 0 0 0, and then a 1 1, and then let's say 0 0, right? Then what would have happened is that over here I would have tried for this and for this, right? Then this would have tried for this and for this. This would have also tried, right? So on and so forth. The complexity would have actually become 2 to the power n. Then you would have actually utilized a DP over here to store the states. And then it would have become way more complicated. That's one way of doing it, but it's way too complicated. Now, the reason this approach is still giving us a valid answer is because, let's say, if I'm able to move from here to here, right? So from this node, let's say, if I'm able to move to this node, right? It actually gives me the similar answer as even if I'm moving to this node, because in both the scenarios, let's call this node as X, let's call this node as Y, right? In both the scenarios, even if I'm at X or if I am at Y, my possibilities of the next node does not changes. From X also, I can go to go to A and B. From Y also I can go to A and B, right? So the possibility actually doesn't changes. The only thing that over here matters is that if my X itself was a trap, then I should have checked it and I should not have tried it itself. So that's what I'm doing. So if it's not a trap, I can utilize it directly. Make sense?
Yeah, right.
Cool. So if that's fine, I would like to move on to the next topic. But since you guys wanted to cover DFS, so I just wanted to know if the concepts are clear or any doubts you have. Anyone? Cool enough. So if there are no doubts, I'll be moving ahead now. Okay. Cool. So let's discuss a new thing that is known as DSU. So what is DSU? This is also called disjoint set union, or it's sometimes called union find. Now, if you're gonna sit for a substandard company, I shouldn't be using that word, but yeah, if you're gonna sit for a service-based company and not of one of the top-notch companies, probably you're not gonna face questions from this particular topic, because this is considered like a hard concept. Although it's definitely not a hard concept, but still it's like deemed that way. But it's anyway a very simple concept. I'll try to explain this concept first, and then we'll try to look at the code also. So what it states is that, let's say this is a graph you're having, right? Okay, there's something like this. Then whenever I'm at any node, so I'll give you any node. So I'll say that, okay, so you firstly have to make components. So you'll say that this is the component A, this is component B, this is component C. Let's talk about some real life examples. Let's say on my Discord server. So this is my Discord server. 3 of you are friends, right? So you 3 are connected. You're actually friends. 2 of these guys are friends. Then there's a person who's not a friend with anyone, right? And there's another node. And let's say these 2 becomes friends now, but this is not a friend to anyone, right? So now in this scenario, we can assign groups, right? So we can say this is the friend circle 1. So let's call it F1. Not the car, but yeah, F1. Okay, F1. This is F2. This is F3. This is F4, right? That's easy. Although we'll look at it that how we do it, but that's easy. But what I want you to tell is that whenever you will be standing at a particular node, you should tell me that which friend circle do you belong to, right? And one more thing. Now let's say there's another person who enters this our Discord server, right? And now he's friend with both you and you, right? So he's friend with you as well as him. So technically your friend circle now merge, right? So F1 and F2 would now be making a single friend circle. So we have to also incorporate this kind of information. And I want that whenever you are performing any kind of information, any doubts? Okay. So also I want whenever you are performing any kind of operations, it should be in order of 1 time, or the average time or the worst time, it should be order of 1. You shouldn't be taking like order of n time or something of that sorts. So how do we do it? So that is the actual question. How do we do it? So what I can say is over here also we have an example. So let me show you the presentation itself. So over here, this was the node, right? So the way we defined the friendship is that I said that, okay, 1, 2, 3, 4 and 5 are actually friends. So whenever you ask me that who's the friend of 5, so technically 5 is just limited to 4, right? But so it would have said I'm a friend of 4. But when I would have asked 3, it would have told me that I'm friend of 2, right? So I could have like thought that, okay, 5 and 4 or 5 and 3 are in different friend circles. Technically they are in the same friend circle. So I just want to reach to a node point. So I'll keep traversing it until I reach a end, right? So from 5 I'll go to 4 to 3 to 2 to 1. So if I'll say that, okay, I'm a friend of 1, 1 would also say that I'm a friend of 1, right? It's a self loop. I'll just try to, okay, yeah, oh, that's more visible. Okay, so 5 would also say, 4 would also say I'm a friend of 1, 3 would also say I'm a friend of 1, 2 would also say that I'm a friend of 1. Good enough. The problem in this approach is that, let's say this node was pretty big. So there were n friends in this fashion, right? So let's say there were n friends like this, right? Now when I would have asked this particular friend that, okay, whom are you a friend with? So he would have said that, okay, let's traverse, let's see whom I am a friend with. So he would have traversed all the way till the end. It would have taken in order of n time, right? To this node, it would have taken him order of n plus 1 time, right? So if I would have asked the same questions or the same question to every node, it would have taken me n plus n minus 1 plus n minus 2. That basically is order of n squared time, right? We want to avoid this. So how do we do that? We also want to know that who your end friend is or who the head friend is. Let's just call one to be the head friend because every friend is actually pointing to him. But we also want that this should be doable in order of one time. So whenever I ask a node, it should tell us that okay, if one is my friend in order of one time itself. So that's the entire thing. How do we do it? One thing we can do over here is that we can change the relationship itself. So I'll say that okay, 2 is pointing to 1, good enough. I'll say 3 is also pointing to 3 is also pointing to 1 itself. We'll change the relation. So we'll bring 2 over here, we'll bring 3 over here, we'll bring 4 over here, we'll bring 5 over here. But wait, you'll say that okay, to do this operation you need order of n time. Technically right. So we need order of n time to do this operation, but you'll only be doing this once. So when I'll say that find the friend of 5, you'll technically perform this operation. This operation can be performed in a single recursive operation. So I'll say that okay, from 5 go to 4, 2, 3 to 2 to 1, and while we would be returning back from a recursive path, we would make the changes that would perform this particular scenario that would directly link each of these members to their parent, right? So this is all about DSU. Now even this could sound complicated to you, but the code is so simple and so elegant that you'll actually love it. I'll just have to check that whether if I have this code. Okay, let me see code snippet for union. Okay, that wasn't what I expected. Okay, I don't have the code snippet for union, but I can use it if you require. Give me a second. Anyway, let's type it up. Union find code. Okay, I don't want to use this. I don't want to use this. CPL Go has it. Okay. See, this is the code for union find. So I'll explain the code itself. So firstly, I want to set unions. So there are 3 methods in total. So the first method is make set. What does make set mean? So make set means okay, that would be a bit complicated. But anyway, how do I teach that? Give me a second, guys. Okay, find that basically means find the parent of node B, right? Okay, top hierarchy friend. Okay, there could be a okay. I'll make a set. That's fine. Then I'll find a set. That's also fine. Then I'll say union set. Cool enough. Okay. So guys, you still here with me? Shall we start this?
Yes.
Okay. Okay, cool. So let's start this. So there are 3 methods in total. Let's not bother even about this. Right. So let's just say there are two methods. So the first method is find the set. What do I mean by that? So I'll be giving it a value and you'll have to find that who its best friend is or who's the top hierarchical friend. So what do I mean by that? So over here, 5 was saying that the friend that is present at the top hierarchy is actually 1. So when I reach out to 5, I should get the value as 1 itself. Cool enough, I can do that. So find set just returns me the top hierarchy friend, or you can say the topmost friend or the value of the group itself, because 1 over here is actually denoting the group, right? Cool enough. Okay. Yeah. Then we have something on union sets. Now what is this? So this is the same scenario which I discussed over here. That okay. Yeah. So when you have addition of a node, right? So this node got added, right? The pencil isn't working now. Awesome. Okay. Anyway, so a new node got added. Now you want to tell us that okay. So you are node A. Or new node B became your friend. Became your friend. Right. Now you want to establish a relation between the node A as well as node B. So in order to do that, you'll use the function union set, right? So in union set, you'll say that okay, A. now is a friend of B. But how would you do that? So firstly, you'll have to find the parents or the top hierarchical friend of both these nodes. So this is the top hierarchical friend of node A. Top hierarchy, let's call it friend. Okay, friend of node A, right? This over here is actually the top higher friend of node B, right? Now we'll check if both of these nodes, now it's possible that you already were in a friend circle, but you still didn't know who's your, like if you're connected. So that would be given by when you'll check for your top hierarchy friend. Now let's say we were talking of node 5, okay, over here. Let's say we were talking of node 5 as well as for node 3, right? And we were saying let's make them friends because we didn't know that they already are friends, right? So we'll say that let's make them friends. So firstly we'll ask node 5 and 3 that get us your parents or get us your top hierarchical friends. So 5 would return us 1 and 3 would also return us 1. In that kind of a scenario, A would be equal to B. So let's change the name over here. Let's change it to PA and to PB. Okay. So this is PA is not equal to PB. Then only do this. Equal to PA. Cool. Okay. So in case the top hierarchical friends of both these nodes were same. So if PA is equal to PB, then continue or just return, because I don't want to do anything. Don't do anything because they're already in the same group. But in case they're not in the same group, then what would happen is that parent of PB or this value or PA would not be equal to PB. So in this scenario, this would be a scenario like you are asking for a friend 3 and you are asking a node 8, right? You are saying that let's make 8 and 3 as friends, right? I can do that. But would I directly connect 8 with 3? No, I won't do that. What would I do is that I'll ask for the top hierarchical friend of A and the top hierarchical friend of B called PA and PB, and then I'll make the top hierarchical friend as PB, PA, right? So I'll make the top hierarchical friend of PB as PA. Now I was using terms of friends and stuff. That's why we were talking about top hierarchical friend and stuff. But technically, in terms of graph, we always try to use the notation parent, right? So it becomes like a family tree, right? So that's what we actually use. So we'll say the parent of PB is now PA. That's entirely what a union find is. So there's nothing more related to it. So it's not like magic. If you want, I can show you the code up and working, but that would, I guess, be a utilization of more time and won't be constructive enough. But if you want, I can show you that. Or if you want, you can we can end the session right over here, and I could give you a few more questions. What do you guys want? Were you able to understand how DSU works? And the code also is fairly simple. I'll say I don't think you would have seen a smaller a code that is actually smaller than this, right? So the code is small. The utilizations or the utility is immense. You can use it at a lot of locations. So I'll say if just like a 10 line of code or 11 lines of code is giving you so much of utility, you should definitely use it and you should definitely practice questions from this. Make sense? And more so, it actually appears at a lot of places, at a lot of good companies. So when they're having interviews and stuff, so good companies tend to ask questions from DSU, from segmentaries. I've already taught segmentaries, but they'll be asking you questions from DSUs as well. So with that, DSU is completed. I do plan of giving you questions and explaining and teaching more questions from DSUs, but I didn't want to club that in this particular session, else this session would have become pretty big. So I didn't want to do that. So other than that, anyone of you has any doubt? I hope I didn't rush it.
Sir, actually, sir, yeah, sir, I know, sir, how to implement this. All these things is good, sir. But sir, in front of questions, sir, I don't think that actually that question is developed by the DSU or any other. I think alternate routes. Not able to get that the question can be by DSU.
Bro, your voice is actually breaking a lot. I'm not able to understand the exact doubt. Can you type it please on the chat?
Okay, sir, let me type it.
Sure.
Okay.
Anyone else whose mic is working, or if your mic is not working, you can always type it out. Okay, let's just wait to hear the doubt. Okay, in this code all, please I saw the path compression, or isn't that important? Is this code all? Yeah, this is actually all. So okay, let me show you what you're talking about, the path compression, right? Okay, got it. Yeah, the path compression is actually missing over here. So the path compression goes on like this. Now I don't know why they had not mentioned the path compression. The path compression goes on like this. Good point. I'll anyway explain this. So this is important actually. So what would happen is that, let's say, okay, so I'll just type it out. 5 was connected to 4, right? 4 was connected to 3, then 3 was connected to 2, and then 2 was connected to 1, and then 1 actually had a self edge, right? Let's just call it a self edge, or it was connected to 1 itself. Let's just call it this way. Thanks, Anur. I'm assuming your name is Anur. So thanks for bringing this up. I'll explain this. Cool. So what happens is that from 5, you tend to go to 4. Then from 4 to you'll go to 3. You'll go to 2. Then you'll go to 1. As soon as you reach 1, you'll say that my value is equal to my parents' value. So that means I am pointing to myself. So I am the top hierarchical friend, right? So I'll return my value from here. So 1 would actually return 1. Cool enough. So I want now that 2 should say that my parent is 1, right? That's fine. But what should 2 return? So 2 should also return 1 itself. So the value you are going to return should come from a parent itself, right? So 2 is now going to return. So also the updations we are doing, I'm going to save it over here. So 2 is now saying that my top hierarchical friend is 1. It will return the value 1 itself, right? So now 3 would also say that my top hierarchical friend is 1. Cool enough. It will return the value 1 also. So now 4 would also say that my top hierarchical friend is 1, right? And would return a 1, right? And then 5 would also say that my top hierarchical friend is 1, and then it will return a 1 also. So this is the way it gets populated. So this line is actually pretty useful. I don't know why they had not mentioned it, but yeah, this is one of the most important things. So you have to mention it over here. If you would not perform this, so technically the way this is getting performed won't happen, right? So every time you'll have to traverse through this entire graph, and then you'll time complexity would be order of n square. So you don't want that, right? So you want this kind of a scenario wherein all the nodes start pointing to the right parent. So this is done by this logic. So you just have to write parent v is equal to find set of your parent. So that's how it's done. Thanks for bringing this up. I actually missed it. Cool. Any other person has a doubt? Okay, cool. So okay, what are the list of topics in the whole graph data structures for CP and interview perspective other than DSU and DFS? Okay, so see, if you have done DSU and DFS, next thing you need to do is BFS, obviously. After BFS, you can move on to Dijkstra. Dijkstra happens to be one of the most important algorithms, I'll say, because its usage is immense, right? Like I said, that DSU can be utilized at a lot of locations. And whenever you are going for a shortest path or something of that sorts, Dijkstra becomes one of the most important algorithms you can use. Dijkstra is just a basic change in compared to BFS. So in BFS we use a queue. In Dijkstra we use a priority queue. That's it. So that's the difference. So I can teach BFS in Dijkstra in the list session, and that would be more complete than this, because today I wanted to teach two different concepts, so I had to rush a bit. But when I'll be teaching BFS and Dijkstra, so they're almost related, right? So the only difference is using a priority queue versus a queue. So I'll be teaching that. Other than that, I'll not say there are such concepts that you need to learn for placements per se. Yes, for CP there would be ton of concepts that you can learn. But for placements, these are more than sufficient, I'll say. You can go through some more concepts like prisms and cruscals. But frankly speaking, in my entire placement session, I sat for more than like 50 companies, and I actually cleared most of them. But I didn't see a single questions from these algorithms. And there are more complicated algorithms, like there are bridges, then articulation points. Then you have a lot of stuff basically. So the list is pretty big, but these are the basic stuff. Yes, after we have done this, we can talk about articulation points and bridges. That is something I want to teach. That is a good algorithm, but it's hardly used, right? Like you really like it's really rare to see such questions. Then you have Target's algorithm, strongly connected components. So the list is pretty big. But yeah, we'll cover it. Don't worry about that. We'll cover it. Slow and steady wins the race. So we'll be following the same path. Cool. Other than that, any doubts? Who's Schrodinger? Nice name, bro. Whosoever you are, nice name. Studenja is about to speak, right? You want to speak something? Cool. So, yeah. Okay. So if no one has a doubt, thanks Jay or thanks teams. Qubit has it. Okay, thank you. Cool guys. I hope this made sense to you. I'll try to post a few questions that you can do and where BFS and DFS can be applicable. Oh, sorry, I missed out on the doubt from Abhi. So Abhi was asking that I'm saying that how to know that this one is DSU. So okay, so DSU when you are talking about things and wherein you are to find or you have to make groups, right? And you have to assign them an ID. So most of the time, what people do is that they'll try to use a hash map or that stuff, and then they'll get a TLE or a MLE or like anything of that sorts, right? So in those kind of scenario, you should know that you're gonna use a DSU. DSU is mostly used in such scenarios wherein you have to make groups and you have to give them an ID, right? And then there's some complicated usage of DSU also, like offline DSUs over there, but those are I'll say a bit of high level stuff. I don't expect them to come at a beginner level questions, or I don't expect them to come at somewhere around 1500 1600 level at code forces. You can expect them to come at later stages, so don't worry about that right now. But at DSU would come in handy wherein you'll have to make groups. Other than that, always try. So if you're not able to think, if you can convert a particular problem into a graph problem, the thing is you have to visualize it in terms of graph, right? Instead of cells, start thinking about nodes, right? If you're able to think it in terms of nodes, and you think if you're gonna traverse it and it's gonna make sense, then just go for this method. Cool, that makes sense, I guess. Cool guys, thanks a lot. Bye bye. Also, a quick announcement. So we'll be having a session on permutations and not permutation, mathematical permutations, but I'll be teaching that how do we make permutations and subsets from a array, right? So given a array, if you want to make some permutations or you want to generate all the possible subsets out of it, how do we do that from recursion itself? So Abhay Chauhan had already asked me, but he has been asking that question for a while now. So I'll be hosting this session, and that session would be conducted maybe like 10 minutes from now. So you can take a break and come back over here. I'll be definitely going a lot in detail over there. So I'll be dragging the code and stuff. So if you're a complete beginner, that session actually could help you a lot. Cool. With that, I'll like close this video now. Bye bye.